And for this one, I'd like to bring on Marek to tell you about an incredible thing that they've managed to make go live on the Celo network. So to talk about the Eclair Testnet, please give Marek a big round of applause.
Thank you. Hey, everyone. It's wonderful to be here. And it's, I think, extra fun to be following Sergey with some 8-bit graphics, some 8-bit JPEGs that I will not be selling to you. So don't worry. But, I like to try to make my talks fun. And so this is a talk in the style of Zelda. Any Zelda players here growing up? Okay, a few of you. And so I'm here to celebrate with you guys a pretty exciting milestone. And so just yesterday, we launched the Celo Eclair Testnet, which is really a first of its kind. It's the first public network to be using SP1 in combination with EigenDA, specifically EigenDA v2. And so if you like this talk, definitely come find me afterwards. You can ask me some questions, but I'm also available on Twitter. My DMs are open at Marek _. And so we're really excited to be talking about Eclair right now because, as many of you probably know, Celo just transitioned from an L1 to an L2 earlier this year. We transitioned to an OP stack-based L2 using EigenDA for data availability. And we haven't been, sitting idly since. The team's been really hard at work thinking about what's next. And so Eclair is really the kind of preview of where Celo is going now that we've become an L2 and now that we're in kind of the Ethereum family. And along kind of the way to becoming an L2, I got a lot of questions from a lot of people asking, why are you going with an optimistic stack? Why are you not going straight to the ZK EVM route? When we announced that we wanted to transition to become an L2, that was roughly 2 years ago. At that point already, there were some early pioneering ZK EVMs that were just going into production. And a lot of people were asking us, why are we going with kind of yesterday's technology and not looking at the future and kind of leaning into ZK? And the reason for that is, we looked really closely at some of these ZK systems, and we realized that, they were actually very complicated and very difficult to maintain. A lot of them had, obviously, a lot of handwritten circuits, but they also had their own bespoke assembly languages, and oftentimes the EVM itself was written in that assembly language. And so a lot of people had to handwrite, assembly language, the whole, imagine re-implementing all the geth in assembly and then maintaining that through every Ethereum hard fork. That looked like a big nightmare for us. And so instead, we had this hypothesis that ISA-based proving systems would become efficient over the course of the next few years. Again, this was 2 years ago. And if you fast forward to today, the hypothesis has really played out. I'm sure many people here are familiar with Succinct and RISC-0. I would say about half a year ago, these systems finally became cheap enough that you can actually use them economically for a ZK EVM. And that means, you no longer have to write your ZK EVM in this complicated assembly language. You can simply write it in Rust, compile Rust to, say, RISC-V, which both Succinct and RISC-0 can improve with, and then you can use one of these two systems to effectively prove your machine code. And that makes it so much easier to maintain your code and to continue to track Ethereum as it continues to get better and hard fork every year. And, what's even more exciting, I would say, than the fact that, this hypothesis has played out is the fact that we now, as of really only a few weeks ago, have something called real-time proving. Anybody here following this trend? It's pretty exciting. So, as of really, again, only a few weeks ago, it's now possible. SP1 kind of announced their Hypercube proving system that can actually prove Ethereum blocks in under 12 seconds. So previously, it could take initially half an hour to prove a block. And all of these systems and Succinct especially have been working really hard to lower these latencies, and they've lowered them down to the point where you can actually prove a block faster than the slot time of Ethereum. And so that means, of course, that you could then submit these proofs for every block so that your L2 could have, near instant withdrawals through the native bridge. But it also unlocks something called synchronous composability, which will effectively allow anyone to transact across rollups and L2s and between mainnet and rollups and L2s effectively synchronously. So you'd be able to submit transactions on two networks and have them be guaranteed to execute atomically. And so that will allow a level of composability across all of Ethereum that we're all really excited for, and I think ultimately will help us make Ethereum feel like one giant chain instead of kind of this amalgamation of many different chains. And so we're really excited for this future. It's coming, I think faster than we even expected and predicted. And so in order to get ready for this future, we wanted to start leaning in and start doing more and more with ZK. And so, since there is no Eclair emoji, we took a chocolate bar emoji, we combined it with a hot dog emoji, and this is how we got Eclair. And so we just launched the Eclair Testnet yesterday. It's a short-lived testnet. We're really excited about it. If anybody here saw our prior year's short-lived testnet Dango, we announced it last year at ECC. A few people raised their hands. So you can think of Eclair as similar to Dango last year, which is really a showcase of where Celo is going. We're going to continue working on the code. We're going to continue to get it audited, and then have it go through our typical release process, going through our 2 public testnets and eventually to mainnet, hopefully later this year. And as I mentioned, Eclair is unique in that it's really the first public testnet to be combining Succinct's SP1 kind of proving technology into a ZK EVM that is also using EigenDA for data availability. And I think the combination is both unique and actually quite difficult from a technical perspective. And because this is a Celo testnet, Eclair has a bunch of Celo features. So Celo is fully EVM compatible, but it has a few bonus extensions that allow you to pay for gas, for example, with stablecoins, and that also allow you to use Celo as an ERC20 token and as a native asset. And so Eclair features some of these features, and then it uses specifically OP Succinct Lite on the ZK side. So OP Succinct, we'll talk a little bit more about what this is and how it differs from OP Succinct. But at a very high level, OP Succinct Lite is the optimistic variant of OP Succinct. And so it still is an optimistic chain, but you are actually proving these fault proofs using ZK, using the Succinct's proven network. And then for DA, we're using EigenDA v2. This is a new DA product by the EigenLayer team that just launched just a few weeks ago. And so we're really excited to be one of the first to be playing around with it. And so I'm going to go into more detail for how all of this works. But before I do that, I thought I'd do a live demo. I don't have a blackboard behind me that I can draw on for a beach wedding. So instead, I'm just going to use my kind of transparent keyboard over here. And I'm going to do something pretty fun. So this network is live. And I am here. I decided, why not stress the system? Why don't we challenge one of the state roots that the proposer recently proposed and see if we can trick the network into accepting my fraudulent state root that is different from the one that the proposer is proposing. And so this is what that looks like. I just started the challenger. I just posted a bond. And now the proposer has to respond to this challenge and convince me and honestly the whole network that the original state root that the proposer posted on the L1 is correct. And so we're going to let this sit here during the course of this talk, and we'll come back later and we'll see what happens. Creating this response obviously takes a little bit of time, And so let's give it a moment to keep working on that. And so in the meantime, we can kind of go into a little bit more details for what this network looks like. Once again, we're using both Succinct and EigenDA. And on the Succinct side, as I mentioned before, we're using this light version of OP Succinct. This is, again, similar to OP Succinct regular, but optimistic. And what that means is that you only have to use the ZK system when there is a challenge to the proposer who is submitting optimistically these state roots to the L1. And the nice thing about this is because we're only using ZK when there's a challenge, we're not incurring all of the large CPU costs of constantly proving every transaction. And so the end result is that the transactions that end users pay don't have to pay for this extra compute, which means that we can keep transaction fees low, certainly lower than if you were doing this constant validation, constant proving. And so you get the benefits of ZK while keeping transaction fees still low. The other thing that's really nice is instead of having to go through this very long interactive proving game that's common in these optimistic systems where you're proving where you're basically doing a binary search through the execution trace of the ZKVM, here we can actually do something with just one round of interactivity, right? Someone challenges you and then the proposer can basically construct a valid proof and then submit it. There's only basically 2 rounds. That means that you can complete the whole process in the span of a talk instead of in the span of a week. And so that means that you can actually get much faster finality out of your native bridge. You can withdraw funds more quickly directly out of your native bridge. And then finally, I think proving costs keep going down. Every year they get cheaper and cheaper. And so it won't be long before moving to just a typical ZKVM that does full validation will be efficient and cheap enough for everyone to pay. And so this also provides a really nice upgrade path to that flow. On the EigenDA v2 front, this is a pretty exciting upgrade from the EigenLayer team. EigenDA v2 effectively moved the validation of their quorum certificates from the L1 to the derivation pipeline in the L2. So in the past, every time you wanted to put some data into EigenDA v1, you had to wait until they had enough data aggregated together so that they can amortize the cost of writing to the L1 and verifying that signature. Now you don't have to do the amortization, so they give back a certificate to your data really quickly, within the span of just a few seconds. They've also increased their network throughput, they have more efficient chunk distribution, and critically, they've also implemented this thing called Hokulea, which is basically a re-implementation of their portion of their derivation pipeline that's currently implemented in Go. They've re-implemented in Rust so that you can prove it in the Succinct Prover as well. And so we've integrated Hokulea into Eclair so that we can prove not just the state transitions of our EVM blocks, but we can also prove the authenticity of the block data itself that is actually being then executed. Now, since this is a Celo network, we have some Celo extensions as well. And so, I mentioned this ability to pay for gas with tokens that we support in Celo and the ability to also interact with the Celo token both as an ERC20 token and natively. All of this is implemented in our Go Ethereum client, but Succinct is much more efficient if you prove Rust code versus Go code. And so we've had to actually port some of this code into Rust in order to make this work. And what's nice about that is this also opens the door for us to be able to use Reth in the future, either to have multiple clients on the Celo network or to increase transaction throughput, even beyond the very high throughput that we support today. Okay, so let's go back to this demo. I'm curious how it's progressing. Let's take a look. So it looks like the proposer got back. It generated a proof using SP1. That proof you can actually look at on the Succinct Explorer. And then that proof showed that the previous state route that the proposer proposed was in fact valid, and so the proposer won the game. And so that's bad news for me because I just lost my bond, but you know, it was worth it to show you guys. And it's also good news for the security of the network because it means that, you know, my bogus state route that I tried to trick everyone into accepting wasn't accepted by the overall network. The network kind of did the right thing. It remained secure. And, you know, all of this happened in the span of, you know, less than 10 minutes. I think in reality, it kind of took less than 4 minutes. And so it was really, really quick without kind of many rounds of going back and forth that would be otherwise necessary for an optimistic roll-up. So here's the page on the Succinct Explorer that's tied to that proof. You guys can go and look this up by just going to explorer.succinct.xyz. You can see how many credits it took and also how long it took, although on this screen it's covering the part that says how long it took, so I can't read that out for you. But it was pretty quick. Oh no, it's up there, 54 seconds, yeah, less than a minute, so very, very, very quick. And so you might be wondering, okay, what did all of this look like? And so I have a little block diagram here to kind of explain it for you. So here we have the L1 chain and the L2 chain kind of progressing. At some point, the proposer wants to move or to capture the state route that exists on the L2 chain on the L1 chain, and it wants to do that again optimistically, and so it's just writing the state route to the L1. But you know, someone like me can decide to do a demo on stage and challenge this proposal. And if that were to happen, the proposer has to quickly get into proving mode and actually come up with a proof to respond to this challenge, because if it doesn't, then the challenger wins and the challenger's state route becomes the valid state route. And so in this case, you know, we fire up SP1 and we start generating those proofs. And we're doing a couple of things. We're proving the state transition of all of the blocks on the bottom. So we're proving every transaction. We're proving every state change that's happening, every update to the Patricia tree. All of that is now happening, you know, using the SP1 prover. But the other thing we have to do is we have to verify the validity of the actual data going into these blocks from EigenDA. And I mentioned that this is the kind of the complicated piece. That data is stored off-chain, but the public keys of the operators that are signing those certificates that I talked about before, those are stored on-chain in the L1. And so we actually need to read from the L1 as well, and we need to construct a proof that proves that the public keys that exist on the L1 in aggregate match the signature that exists on the data that's coming from EigenDA. So we actually are checking that a quorum of those operators signed off on that data, and then that data was used to create these blocks that, again, we're running these state transition proofs on down below. And so once we do that, we can construct a proof. We can respond to that challenge, again, on the L1. And that proof can then be verified, you know, in a constant amount of time on the L1. And that effectively allows us to then respond to that challenge with hard evidence that the challenge was wrong, and in fact, the previously supplied proposal was correct. And so that's in effect what I just showed you with that demo. Again, running kind of in the background over the course of this talk. It's pretty cool that it's that quick. Again, much, much faster than what you're seeing with a traditional optimistic roll-up today. And then once that's done, then, you know, the check marks below kind of correspond to kind of the state of the chain that is visible through the L1. And so we basically now assume that all of those blocks now are represented in the L1. So yeah, I think that's really everything I have for you today. You know, we're super excited about this. Again, it's a big milestone for us. We worked really hard ever since the L2 transition to ship this, and we're so excited to have done that this week here. We got to celebrate with some actual French eclairs, which was pretty fun. And we're really excited about, you know, bringing this to production. So just like last year with the Dango network, we're going to go through the standard audit processes, release this through all of our test nets, and hopefully by the end of the year, ship it to mainnet. We're super excited, and we hope you are too. Thank you.